Imagine holding a city in the palm of your hand. Not a model, but a real city, teeming with activity yet shrunk down to the size of your fingernail. This is the incredible reality of a computer chip. Under a powerful microscope, the chip's surface transforms into a bustling cityscape. We see intricate circuits like highways and byways connecting billions of tiny transistors. These transistors, acting as electronic gates, are the lifeblood of the digital world. They switch on and off billions of times per second, directing the flow of information that powers our computers, smartphones, and countless other devices. This microscopic metropolis is a testament to human ingenuity. The scale is staggering. A single chip can contain more transistors than there are stars in the Milky Way galaxy. Each transistor is a marvel of miniaturization, measuring just a few nanometers across. That's about 1/10,000th the width of a human hair. And yet within these infinitesimal spaces, complex calculations and data processing occur at lightning speed. The chip is a testament to our ability to harness the power of the very small to achieve extraordinary things. The production of these miniature cities is a global endeavor. Specialized fabrication plants known as fabs hum with activity around the clock, churning out trillions of chips each year. These fabs are more than just factories. They are temples of precision engineering, where the air and water are meticulously filtered to prevent even the tiniest dust particle from interfering with the delicate manufacturing process. The demand for chips is insatiable, driven by our ever-increasing reliance on technology. Every smartphone, laptop, car, and even refrigerator now relies on these tiny marvels. The global chip shortage of recent years has highlighted just how crucial these components are to our modern world. The intricate supply chains stretching across continents are a testament to the complex dance of globalization and technological advancement. At the heart of chip manufacturing lies a process called photolithography. This technique, akin to sculpting with light, is how we build these incredibly complex structures on such a minute scale. Imagine using a beam of light to carve a statue, but instead of marble, you're working with materials 1,000 times thinner than a human hair. The process begins with a silicon wafer, a thin, circular slice of highly purified silicon. This wafer acts as the foundation upon which the chip's intricate layers will be built. A light-sensitive material called photoresist is then applied to the wafer's surface. Using a stencil-like mask, ultraviolet light is shown onto the photoresist, selectively hardening or softening specific areas. The exposed areas are then chemically etched away, leaving behind a precise pattern on the silicon wafer. Section 4. Building the Silicon Metropolis, a step-by-step journey. This process of photolithography, along with other crucial steps, is repeated hundreds of times to create the layers of a chip. Each layer builds upon the previous one, adding transistors, interconnects, and other components that give the chip its functionality. First, let's talk about oxidation. After the initial photolithography step, the exposed silicon is subjected to a high-temperature process that creates a thin layer of silicon dioxide. This oxide layer acts as an insulator, preventing electrical current from flowing where it's not wanted. Next up, ion implantation. Precisely controlled beams of ions are fired at the silicon wafer. These ions, typically boron or phosphorus, alter the electrical properties of the silicon, creating regions that will become the transistors. Now it's time for metallization. A thin layer of metal, usually aluminum or copper, is deposited onto the wafer. Photolithography is used again to etch away excess metal, leaving behind the desired interconnecting wires. These steps are repeated layer upon layer, with each layer adding more complexity to the chip's design. The transistors are connected to form logic gates, the building blocks of digital circuits. These gates, in turn, are interconnected to create more complex functional units, like memory cells and processing units. Section 5. Sustainability in the Silicon Age. The intricate process of chip manufacturing comes at a cost. The fabrication plants require vast amounts of energy and water. They also generate significant amounts of chemical waste. As our demand for chips continues to grow, so too does the environmental impact of their production. However, the industry is not standing still. Efforts are underway to make chip manufacturing more sustainable. New materials and manufacturing processes are being developed that require less energy and water. Recycling programs are being implemented to recover valuable materials from used chips. and companies are working to reduce their greenhouse gas emissions. The future of chip manufacturing lies in finding ways to meet the ever-increasing demand for these tiny technological marvels while minimizing their environmental impact. It's a challenge that requires innovation, collaboration, and a commitment to sustainability. As we continue to push the boundaries of what's possible with technology, we must also be mindful of the resources required to create it. The future of our planet may depend on it.